Let's continue our discussion of work. We're using integrals to compute the amount of work performed by either a variable force, or we want to consider problems where maybe the force is constant, but the displacement of the object is not constant. And this might seem a little bit strange. How can we move an object at a non-constant displacement? But we'll see that really different parts of the object are moving different distances. So let's take a look at an example where the force really is constant, but the displacement is not. Take a look at example 3. We have a 100-meter long chain with a mass of 50 kilograms hanging off the edge of a 150-meter building. We're imagining taking the entire chain and coiling it up to the top of the building. We want to know how much work is required in order to do this. Now, we ordinarily think of this as sort of a continuous process. Maybe the chain is on some sort of a coil and we wind it up to the top of the building. But it's going to be really useful here to think of doing this discretely, taking one link of the chain at a time and moving it to the top of the building. And we'll see how thinking of the problem in this way helps us to solve it. So let's start by drawing a picture. Here's our building. It's 150 meters tall. And really, we just need to know that it's longer than the chain. So here's our 100-meter long chain dangling from the top of the building. Now, we need to move the entire chain from where it is to the top of the building. And the way to think about this, it seems a little bit strange at first, but think about it as moving individual portions of the chain, individual links. So the first link of the chain, that's very close to the top of the building. We don't have to move it very far. We just have to move it just not even a meter. The very last link in the chain is 100 meters from the top of the building. We have to move this last link a great distance in order to get it to the top of the building. So instead of thinking of coiling this up continuously, think of independently moving the different links to the top of the building. The chain near the top of the building doesn't have to move very far, so we're not going to do very much work for the top portion of the chain. The chain that's near the bottom of the building needs to go much farther, so we're going to perform more work for this portion of the chain here. The weight here is the force that's involved, and the weight of the chain really doesn't change. But the distance that we're moving the chain, that is what's changing here. So in order to solve this problem, we're going to think of some small slice of chain. And really, it's helpful to think of a single chain link. So we're going to take a small slice of chain, and let's say this is a distance x from the top of the building. That's how far that slice needs to move. And what is the width of this slice? Well, if we're measuring a distance x from the top of the building, then the width of this slice will be some small distance dx. So we're taking this small slice of chain and we're imagining just taking this slice and moving that to the top of the building. How much work is performed only on this slice of chain? If we can find an expression for the amount of work performed on a slice, we can integrate to find the total amount of work. So how much work here is performed on a single slice? Well, let's call this dW for some small amount of work. And the work is the force times distance, x. Now, if we were to zoom in here on this small slice, really the top of the slice is a little bit closer to the top of the building than the bottom portion of the slice. So really, we don't even have a constant distance unless we slice it up infinitesimally thin. So using x as the distance, we're imagining slicing up so thin that the displacement or the difference between the top and the bottom of the slice, that's negligible. So this x distance is really the distance for the whole entire slice. All right, so we have an expression here for the work performed on this slice, but we need to get this all in terms of numbers, in terms of x, so that we can integrate. So force is the weight of this slice. That's the force that's involved here. Force is the weight, and it's important that we think of the weight only of the slice, not the weight of the entire chain. We're only interested in this small slice of chain. So what is the weight of the slice? Well, we're working here with kilograms, and so we need to convert from mass to weight. So we first need the mass of the slice, and then we're going to multiply by 9.81, the acceleration due to gravity. I was calling this the gravitational constant earlier. Gravitational constant is something else. This is the acceleration due to gravity. This is small g. The gravitational constant is large g. So I was calling it the wrong thing, but here we have acceleration due to gravity. Now we need an expression for the mass of the slice. Well, we know that the length of the slice is dx, but that's not the mass. In order to find the mass of the slice, I'm going to multiply the length of the slice by the density. So this is something that we haven't used yet in the problem. We were told that this 100-meter long chain has a mass of 50 kilograms. So we have a 100-meter long chain and its mass is 50 kilograms. We can write down the density here as mass divided by length. 50 over 100. The units are going to be kilograms per meters. So the density of the entire chain is 1/2 kilogram per meter. Now let's think of units here. Mass should be measured in kilograms, and dx over here is going to be measured in meters. That's a small change in distance. So this has units of meters. I can find mass by multiplying meters times density. The units will work out. So to get the mass, I take the distance, the length of the chain, dx, times the density, 1/2. Again, let's think of units. dx has units of meters, 1/2 is the density, that's kilograms per meters. When we multiply kilograms per meters times meters, we get units of mass. So it's important here to keep track of units, and that helps us to see how to get the different values we want. This is probably the trickiest part of the problem here. In order to get the mass of this small slice of chain, we multiply the length of that small slice, the dx, by the density of the overall chain. Once again, we're only thinking of the small slice. We're not thinking of the overall chain. So we have the length of the small slice times the overall density. That will give us the mass of the slice. This is still times 9.81 times x. And let's think of units here as well. 9.81, this is meters per second squared. X has units of meters. If we take all of these units together, we'd have kilograms times meters per second squared times meters. These are units of joules. So we are getting units for work. This is the amount of work performed on one representative slice of chain. Once we have this, we simply need to integrate to find the total amount of work. So to find the total amount of work, we integrate the expression dw. So we are integrating 1/2 times 9.81 times x, and we'll put the dx here at the end. We integrate for the entire length of chain. So x is the distance from the top of the building. We need to start integrating at a distance of 0 to get the top portion of the chain, and then we need to continue integrating until we get to the total length of chain, which is 100 meters. So the limits of integration will be from 0 to 100. So this integral describes the total amount of work required in order to move the chain from where it is, suspended in space, to the top of the building. This is a very easy integral. We really have some constants here that we could pull out, and we're just integrating x. So we'll skip the details of evaluating the integral, but the number that we get here is 24,525, and this has units of joules. That's the total amount of work required in order to move this chain to the top of the building. Notice that we can't simply find the amount of work by multiplying the weight of the chain times the distance 100, because not all of the chain is being moved the total distance 100 to the top of the building. We must use an integral in order to solve this problem. Let's take a look at example 4. Notice that example 4 is actually quite similar to example 3. We have the same length of chain, has the same mass, so the density will be the same. The only difference is now the chain is suspended from a shorter building, 80 meters. And the effect is going to be that part of the chain is coiled up on the ground, and part of the chain is suspended in the air. So we want to know how much work is required in this scenario. So once again, we'll draw a picture. Here's the building, which is shorter now, only 80 meters tall. And now the chain is, again, like it was before, except 20 meters is coiled up on the ground because the entire length, once again, is 100 meters. So again, we have a 100-meter long chain. The mass of the entire thing is 50 kilograms. We can write down the density again. This will come in useful. The density is 50 divided by 100, which is 1/2 kilograms per meter. That's the density. Now we have two portions of work that are being done. Let's say work 1 is the amount of work performed on the suspended portion of chain. And work 2 is how much work is done for that coiled up portion. So again, we think of this rather differently from how we would normally think of coiling up a chain. We think discretely. Instead of continuously coiling up this chain, we think of moving the individual components from where they are suspended in space to the top of the building. So for this coiled up portion, we'd simply want to think of taking 20 meters of chain and moving it from the bottom of the building to the top. So for the coiled up portion, we have a constant distance and a constant force, which is just the weight. So this portion of the problem, the second amount of work, is actually going to be the easier. So let's focus on finding the amount of work performed on the suspended portion, which will be quite similar to the last problem, but we'll work through all the details again. Once again, we move a distance x from the top of the building, and we imagine taking a small slice of chain. The width of this slice, or the length, is dx, some infinitesimally small length. We want to know how much work is performed on this small slice. Well, this is some small amount of work dw, and work equals force times distance. The distance that this small slice is being moved is the distance x, and the force, once again, is the weight of the slice. Not the weight of the entire chain, but the weight of the slice that we're interested in. Weight, once again, is mass times gravity, 9.81 meters per second squared. And mass, once again, can be found by taking the length times the density. Once again, let's think about units here. Length is measured in meters. Density is kilograms per meters. 9.81 meters per second squared. X is the distance, so that's measured in meters. We can imagine canceling units of meters here, and we have kilograms times meters per second squared times meters. The kilograms times meters per second squared, that's units of newtons, that's force. Force times distance, yes, we have units for work. These are joules. So the units are working out correctly. We can be confident that our setup so far is good. The length is the small change in x dx. So length here is the length of our little slice, dx. Density is 1/2 times 9.81. This is the same expression that we had in the previous problem. So the total amount of work for the coiled up portion of the chain, this is work 1, we can find by integrating. So we integrate 1/2 times 9.81 times x, integrating with respect to x. And the limits of integration are going to be now from 0 to 80. That gets all of the small slices of chain throughout the entire chain. So we integrate from 0 to 80. That's the amount of work performed for the suspended portion of chain. How do we find the amount of work performed for the coiled up portion? Well, we have a constant force, which is just the weight, and we have the same distance, which is 80. So for work 2, this is force times distance. No integral will be required here. Force is going to be the weight of the chain. So we have weight, and the chain here is just the 20 meters that are coiled up at the bottom. So weight times the distance, which is 80 meters. And the weight is, well, how do we find the weight? We have 20 meters of coiled up chain, and we know the density is 1/2 kilograms per meter. So we can multiply 20 meters of chain times the density 1/2. This gives us units of kilograms. We need weight, so we multiply by 9.81. And then we multiply by distance 80. Again, let's confirm that the units are working. 20 is a length. That's the length of chain coiled up, so that's meters. 1/2 is density, kilograms per meters. 9.81 meters per second squared. 80, that's a distance, that's meters. We can cancel out meters here. We have kilograms times meters per second squared times meters. Yes, indeed, we have units of joules. So, taking this all into account, the total amount of work here is the sum of these two portions of work. So this is W1 plus W2. If we evaluate the integral and then simplify this number and then add the results, the total number here is 23,544 joules. That is the total amount of work for the entire system, both the suspended portion of cable and the portion coiled up on the ground. Let's take a look at one more of these problems involving a cable or a chain. Example 5, we have a cable lying on the ground that is 10 feet long and it weighs 8 pounds. So we're going to be using imperial units here. We'll have ultimately units of foot-pounds for the answer. We want to know how much work is required to lift one end of the cable 6 feet above the ground. So let's start here by drawing a picture. And I think it'll be most useful to draw the picture as if the work has already been done. So after performing this work, the scenario looks something like this. We have a 10-foot long cable, and 6 feet of it is now above the ground, and 4 feet is still lying on the ground. How much work was performed in order to lift up one end 6 feet like this? Well, once again, we're going to think of doing this in a discrete fashion. Instead of doing it continuously by just picking up the end and moving it continuously, we want to think for each individual portion of the cable, how far was that portion moved? So let's think of a distance here of x above the ground, and we'll imagine taking a small slice of the cable. And once again, the length of this slice is dx. We want to find how much work was done in order to move this small slice of cable to its current position. If we can find the amount of work for a slice, we can integrate to find the total amount of work performed. So we set up this expression. The amount of work for a slice, we'll call that dW, some small amount of work. This is force times distance. Distance is x, that's how far the slice has been moved. And once again, force is the weight of the slice. Now, we want to keep track of units here. Right now, we're measuring dx, that's a distance. This is in feet. We want weight, which is measured here in pounds. We're going to take the overall weight density of this cable. So we know that the cable overall is 10 feet. And we were told that the weight is 8 pounds. So we can write an expression for the weight density, which will be the weight divided by the length. So 8 divided by 10, the units here are pounds per feet. And we can simplify, that's 4/5. So that is the weight density of the overall cable. So to find the weight just of this small little slice, we're not taking the weight of the whole thing. We're not taking 8 pounds. We just want the weight of the slice. We multiply the length of the slice, dx, times the weight density. Let's think about units, make sure that they're working out. dx is a distance, so this is being measured in feet. Density, that's measured in pounds per feet. So the units of feet would cancel, and we would have pounds left over. That's what we want for weight. So the units are working out exactly as we want them to. Now, if we think overall, we have the dx, that's feet, density, pounds per feet. X here is a measurement of distance, feet. So overall, this entire expression has units of pounds times feet, or foot-pounds. That's a unit for work. The units work out. That helps us to keep on the right track. So we have dx times the density. Density is 4/5 times x. That's the amount of work for a small slice of this cable. To find the total amount of work, we will integrate. We integrate these representative portions of work. We integrate 4/5 x dx. And what are the limits of integration? Well, we need to keep adding up work starting at x equals 0, going all the way to the top of this portion that's been lifted in the air. So we integrate from 0 to 6. Let's go ahead and evaluate this integral. We can bring out the constant 4/5, and we have the integral of x dx from 0 to 6. Notice how simple this integral is. It's actually a very simple integral that will allow us to find the total amount of work performed in this situation. The antiderivative of x is x squared divided by 2. So we have 4/5 times x squared divided by 2, integrating from 0 to 6. We'll replace the x with the 6 first of all. We have 4/5 times 6 squared divided by 2 minus 0 squared divided by 2. Simplifying a little bit, we have 4/5. 6 squared is 36. 36 divided by 2 is 18. 4 times 18 is 72. So we have 72 divided by 5. The decimal value for this is 14.4. So our answer is 14.4 foot-pounds. That means the equivalent amount of work done to move one end of this cable 6 feet into the air is equivalent to moving 14.4 pounds 1 foot up into the air. That's what foot-pounds means here. So the total amount of work performed is 14.4 foot-pounds. And these have units, and these have units, and these areas have units of, where was I? Simply going to be a